Okay, we're live. Today we're going to be looking at the 2014 physics exam. So let me share that with you. No one's watching in a minute, but I am running a little bit late because I had to install a new program, which I will probably be using more in future. Okay. So let's just go to the start of this. So last time when I went through the specialist exam, I had to import it into Word, and that causes a few problems that I noticed when I tried to do it for physics, one of which was a lot of the symbols end up turning into gobbledygook because it couldn't convert, it couldn't work out what was going on, particularly with the equation editor stuff. The PDF and the Word do not talk to each other well when it comes to that stuff. Okay, so, all right, so we're looking at the 2014 exam. I'll probably break this up into two parts. And so today we'll be going through the first half. The exam itself is, if you see here, okay, we've got section 1. Let me just check to see if you're seeing what I'm seeing. Yes, you are. Okay, so we got section 1, which is made up of long and short answer questions. We'll probably be doing most of part 1 and 2. Section B is made up of the extended response question only. So part 2 also includes the practical design question, where you have to manipulate and graph data. So I'll probably leave that for next time, but I'll go through most of all of part 1, I think, and some part of part 2 this time. We'll see how we go. I'm scheduling for 90 minutes, so I'm going to get on with this in a moment. Okay, so let's take a look. Okay, so I think it's page 3 is your first page of your question sheet, and then page 4 is the second page. So we're going to refer back to this from time to time to reference equations that you need to get. All right, I can probably do these off the top of my head, but all the same, I'll just refer back to those so you know which ones to use and when. Okay, so section 1, this is generally done more or less in order. So the 4 components of the physics course, motion in 2 dimensions, electromagnetism, light and matter, and nuclear. Structure of atoms, structure of nucleus is the last part. Oh, something's flashing here. I don't know why. Okay, it stopped. Okay, so the first sort of question we're going to get is going to be based off motion in 2 dimensions. So we've got circular motion, projectile motion, momentum in 2 dimensions, and gravity in satellites. So this keeps flashing for some reason, at least on my screen. Okay, proceeding anyway. All right, so first question. The bicycle shown in the photograph below has safety reflectors on its wheels. Each wheel is undergoing uniform circular motion. Explain why the reflectors are accelerating even though they are traveling at constant speed. All right, so let's put on a highlight in here. So let's get a pen. We'll see how this pen function works. All right, what is the other one? The other one is a highlighter. Okay, so we can change our colors. So in the exam, you'll be writing in black or blue pen. So I'm going to write in blue. That blue will do. Okay, explain why reflectors are accelerating even though they are traveling at constant speed. Now, mind you, mention that constant speed. That does not imply constant velocity. All right, change in direction. I actually had another way of which I was going to do this. I was actually going to set up a camera and use a physical copy of the exam and write it all out by hand. It would be a lot more efficient that way. However, that camera did not work when I brought it home. So I'm going to be using this, and I'm going to order in another camera. All right, change in direction. Implies implies change in v implies acceleration is non-zero. That's also refers to Newton's first law. Okay, so hopefully you can read that okay. All right. Okay, that's a bit better. That should be coming up nice and large on your screen. All right, question 2. In a flight archery competition, the aim is to shoot the arrows as far as possible. During such a competition, an arrow is shot with an initial speed of 43.4 meters per second at an angle of 38.0 degrees above the horizontal. When the arrow hits a tree at the same height at which it was shot, so the arrow hits the tree at the same height as which it was shot. Okay, so it's shot above the ground, but it hits at the same point above the ground. So that makes it easy. Basically, what we have here is uni-leveled projection, so I might make a point of that. Okay, so there's some special cases of our projectile motion, uni-leveled and horizontal projection, two of the simpler ways in which to view projectile motion. Ignoring air resistance, that's also useful too. All right, so I'm going to go get my calculator so I can make sure I get these right. They all show that questions, but so we need to set them up properly. But I'm missing my calculator. Just one moment. Okie dokie. So, all right, now referring back to page 3, there's an equation for this, but I think we know this one, so I'm just going to state it. The horizontal component is the initial velocity. Oops, I've lost my tool. Oh, there we go. Actually, let me restart that, sorry. I lost it again. There we go. Okay, ux equals u cosine, and what was the angle again? 38. All right. Now punch that in. Oops. Well, sorry, theta. The formula is theta. Sorry, angle above the horizontal. I've lost it again. Sorry. First time using this bit of software. Okay. Okay. That was just. I'm putting the equation in just for the sake of demonstration. You don't need to necessarily state the equation unless it calls for it, and it's generally it won't get you any marks. Just stating the equation will get you no marks because all you're doing is copying things from the formula sheet. Okay, but let's substitute in our numbers. Now our numbers is 43.4 cosine. I don't know why it does that. Apologies. Okay, sorry. Let's be a feather touch with this. Otherwise, it opens up another tool, which is annoying. 38. Okay. Sorry, I've done this again. One more time. 43.4 cosine 38 equals. Okay, so that rounds off to 3 cent figures as 40. Yeah, it's what we're looking for. So where that confirms that, and it's a 0.4 there. Okay, put a point in there. All right, initial okay, uy equals u sine theta. All right, and then that's 43.4 sine 38. Sorry for my scribbles. I'm not going to bother fixing that up. And as you can imagine, that should be the other number we're looking for. 43.4 sine 38 is 26.7 meters per second. Don't forget your units. Okay, sorry for the messy writing. Okay, I might even see if I can zoom this in a bit more. Yeah, I'll leave it alone for now. There's some of the views. Okay. Determine the total time the arrow is in the air. Use 9.8 meters per second for the magnitude of the acceleration due to gravity. Okay. All right. So couple of approaches you could use. You may have been taught for unilevel projection. So your projectile is, that's a very bad parabola, but I'm drawing it with my fingers. And that's not going to work either. Okay. Okay, so that point there is a halfway point. And that's also the Vy equals 0. So you can work out the time to that point and then double it, and that'll be your time of flight. Or you can use displacement equals 0 and solve the quadratic equation. That's a little bit more tricky. So I'm going to do this one. All right, so all right, at maximum height. Now this only works because it's unilevel, so it spends as much time going up as it does coming down. Okay, max height, oops, wrong thing. Vy equals 0 and t equals half of time of flight. So I'm actually going to incorporate the concept that looks ugly. T equals 1/2 time of flight. So I've included the fact that I'm going to have to double this. All right, so let's think about this. Okay, so the equation, so you can go back to page 3, look at your equations of motion if you're not too sure. Well, one of them is this. Final velocity equals initial velocity plus acceleration times by time. Okay, so final velocity is 0. Initial velocity. Now we're talking about the vertical component here, so make sure you're using the right one. You never mix up your velocity. When you've got a one-dimensional equation, you do not mix up your velocity directions or just your vector directions in general. You have to be talking about the same thing. So we're talking about vertical here. So it's 26.7. Plus. Now, acceleration. If 26.7 is positive, that's upwards. This must be negative because it's down. Acceleration is down, so thereby negative 9.8. And times by 1/2 time of flight. So if you unravel this whole equation in terms of time of flight, you've done everything you need to do. Okay, that looked dodgy because I was kind of holding the mouse at the same time. Let's just fix it up. Okay, that's why that happens. Okay, let go of the mouse and then T. F. There we go. All right, rearranging that. Okay, so minus. Oops, I've got the decimal in the wrong place. Fix that. 20. And I have to keep clicking on the pen when I do that. 0.7. I'll get used to this program eventually. About 10 minutes in of me actually using this. Okay, divide that across. All right, so, pardon me, it's not there. Mic across the room. Okay, TF approximately equals, all right, so 26.7 negative divided by 49 negative. Let's cancel the negatives. My calculator here. 5.45 seconds. Now, I'm not working off any solutions, so I don't think I made any mistakes, and with general idea. But if I might make a transcribe error, copy numbers down wrong, something like that. So it's worthwhile trying these yourself and see if you get different results. Practice makes perfect, as they say. Okay, so and a lot of these things, like, okay, we knew those two were correct because we got the correct answers, but this one we don't know because it's not a show that question. But all the same, when you do the next part of the question, because you actually need the time of flight to determine that, if you get a different answer and you carry through here, they'll mark it correct because it's what we call a follow-through error. You did this correctly. You would have lost the mark here somewhere for getting this wrong if you got it wrong. But if you took your answer in time of flight and used it here, and you used it correctly, even though you had the wrong time of flight and you got a different answer, you've done this part correct. So just a point to note for that. Okay, calculate the horizontal distance. Now we're talking about horizontal. Horizontal is distance equals speed times time. Okay. So, what was our horizontal velocity? Okay, remember that for projectile motion, that does not change if you ignore air resistance. So 34.2 consistent throughout. 34.2 times. Okay, so the last answer, we round that off to 5.45. I'm going to go with that. Now that is rounded, so that's approximately equals. This should be correct through some figures. It would be in their margin of error. Actually, what I'm going to do, I've got the answer for time of flight in here. I'm just going to straight up multiply that by 34.2. And all right. And if you do that, you get 186. Yeah, for 3 cent figures, that's fine. All right. So, I mean, everything was given at 2 or 3 cent figures. Yeah, 3 cent figures for all that. 2 cent figures for, no, 3 cent figures for gravity. So it is perfectly consistent to write that to 3 cent figures. That's what you should write it to. Certainly not more. Okay, identify the range of angles that will give a greater horizontal distance for the same initial speed. Okay. Now, what I assume they mean for this is because he's launching above the ground. All right, so he's launching the projectile. He's above the ground. He's launching it from an angle there. And he's firing up like this. Oops, that's not what I wanted to do. No, I got rid of all of it. Try that again. That's kind of your height above the ground. Now, he's launching up such that it's going to go up like this and come down. All right, now, the launch angle, So this diagram looks, so it's all right for what I'm using with it. I'm freehand drawing it with my finger, so not too bad. I hope you kind of get what I'm showing you here, but I'll try to explain it better than I'm showing it. Okay, so that launch angle, if you remember your launch angle for optimal range when it's on the ground and landing on the ground will be 45 degrees. Now we're coming down and we're going to actually fall all the way back down here. Okay, so basically, okay, to get the maximum angle in that case, if you're landing at a height below what you launched at, the maximum will be somewhere below 45 degrees. Now I think that's all they're asking, wanting for that one. So range of angles to give a greater horizontal, actually, sorry. Well, we've done 45. Now this was at 38. Now, just out of curiosity, if we do 38, if we do something like 37, recalculate these. We didn't actually do 45 to start off with. Okay, so I'm actually doing a recalculation just here. So sorry, you can't see what I'm actually doing. But I just recalculated for 1 degree change. All right, and I got, I'm not entirely sure if that was bigger or smaller. So I'll just recalculate for 30 degrees. That'll be a significant change. And then we can really determine from there. Pardon me. So if you change for the angle, you're changing both the two components that we've got up here. So I'll just show you something while I'm doing this. So for 30 degrees, I've got a horizontal component of 34.66, so 34.7, and a vertical component of 21.7. So the maximum is going to lie somewhere in there, and I'm not entirely sure where it is. So I've gone on one side of it, and I could probably make another exaggeration and go to 45, but the maximum is going to lie somewhere in this range anyway, if I understand the point of the question correctly. I might just have a quick look at this and just move on. It's only a 2-mark question. And what's implied is if you're launching above the ground and falling to the ground, your optimal angle for range would lie below 45 degrees. But we started with 38. So I'm not entirely sure if this is actually optimal already. Okay, so let's have a look at this. Well, actually, what I'm doing is calculating this for uniform motion anyway. But there's something to be said about that. Let's see if I get these numbers right. All right, times. All right, we've got 35. I've got something that's actually smaller. So I'm just going to stick with my my answer that I stated over here, which was identify range of angles to give greater horizontal for the same horizontal distance for the same initial speed. Not them both best. If I understand the concept of the question right, I'm going to stick with that because the tree's in the same position. Actually, I'm not entirely sure if that's really what they're after, but I'm going to leave that one for the time being. It's a little bit ambiguous with that. Although you just punch in a few numbers and see if it's larger or smaller than that. Maybe I'll come back to that question another time. I don't want to overcomplicate. It's only 2 marks. All right, let's just assume it's unit level because they're not really making that point. Let's have a look here. Okay, I'm going to make the assumption they're talking about uni level because that's kind of what this has all been about so far. Then it's that's the easiest way. I'm just I didn't write this exam, so not entirely sure that's what they're talking about. But essentially, that's a quick answer for uni leveled. So I'm going to put an assumption there. Otherwise, it's way too complicated to really do for 2 marks. Assuming uni-leveled, you'll get anything between that 38 and 45 will have a larger range. I wish they put in here assuming uni-leveled or assuming landing at the same height that it fell. Okay, but let's just, yeah, I'm going to go with that. That makes sense in the context of the mark scheme. Okay, the motion of a satellite, such as the International Space Station shown above, can be used to obtain a value of the mass of the Earth. The International Space Station completes a circular orbit of the Earth with a speed of that and a radius of this. This is what I was talking about when I imported into Word. Just a little side note that this stuff gets butchered. That's why I had to get this new program. Because I need a PDF reading program that I can also write with some sort of pen or highlighter. Okay, International Space Station completes circular orbits of Earth with speed of that, radius of that. Determine the mass of the Earth. Okay. All right. Determine the mass of the Earth. 3 marks. All right, so let's look at our equations. So we've got speed and we've got radius. Back to let's look at our circular motion equations up here. Okay. All right, so I'd assume we do use this equation here. V is equal to the square root gm on r. Now this is a 1 for satellites, so this one makes sense. And the gravitational constant we use is 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. All right. Let's write that one out. Now that is the mass of the Earth in this question, because the mass of the large body, not the one that's actually completing circular orbits. Okay, so rearranging that equation, v squared equals g m on r, and isolate m. M equals rv squared on g. Put all the numbers into that. So we've got 7.6 times 10 to the 3. No, wrong one. Okay, try that again. R is 6.8 times 10 to the 6 times bracket 7.6 times 10 to the 3 bracket squared over G, 6.67 times 10 to the negative 11. All right. So now I got an answer of approximately. Mind. All right. Okay, approximately 5.89 times 10 to the 24 kilograms. That sounds about right from memory. All right, well, that's what we got anyway. Moving on. Explain why the center of a satellite's circular orbit must coincide with the center of the Earth. All right, now I'm not going to write things out too much in paragraph form when I write these answers because it's just too difficult. So I'm going to make dot points. But just remember, you need to be writing things out in sentence form, particularly with your extended response question. This one you can probably, these short answer explanation questions, you can probably get away with dot points, but not in your extended response. Explain why the center of a satellite's orbit, let's go inside the center of the Earth. Oh, basically because essentially, yeah, the force of gravity is between centers of mass. All right, I've got an end there. Okay, first point. Second point, centripetal force. It's directed towards the center of circle, the circular path. Okay, implies center of orbit for the two of them to work together. Center of orbit must be center. I'm trouble writing with this. Of mass to achieve uniform circular motion. Okay, there you go. It's on my eye. Okay, moving on. Okay, the Magellan Spacecraft used to use microwaves to survey and create maps of the surface of the planet Venus. Actually, very. I think I watched a documentary on some of the Venus probes. The Soviets sent a bunch of them, but they all kind of burnt up very quickly. And this one, I think, was in orbit, and scanned the surface. Because you can't really see it because of the clouds. And if you go into the clouds, Venus is basically a runaway greenhouse effect, and very thick atmosphere. It's very high pressure, high temperature. Everything that goes in there is pretty much toast within a short amount of time. A few minutes, and then that's about it. So technology similar to the laser airborne depth sounder was used by Magellan to project microwave pulses downwards so they reflect normally off the bottom surface of the layer of cloud and off the surface of Venus. The time difference between reflected microwave pulses was recorded. The diagram below shows the path of reflective microwave pulses. So, all right, it's pretty cool. Okay, at a particular location, the two reflected microwave pulses were recorded returning Magellan It's a difference of time difference of that. The speed of microwave pulses that reflected off the surface of Venus was, okay, so Venus has a thick enough atmosphere that you actually have a slight difference between the speed of light. That's interesting. Because usually the speed of light in air is not the difference between that and a vacuum is insignificant for most applications. It might become important for some applications. I'm not aware of what though. Determine the distance between the bottom surface of the layer of the cloud and the surface of Venus. Okay, now if you think about this, okay, the time taken for the time difference for reflected pulse. So that's the time. That's your time 1, and then that's your time 2. And then if I just change colors here, just for the sake of it, all right, that's the time of the reflected pulse. So that essentially, I'll call that's we would call that distance here. Change something else. Okay, that's D. But if you notice the magenta path I've drawn here is 2D because you go down and up. A little bit more than that because it's got an angle there. But we're going to ignore that. We're going to see it's kind of flat. Let's go black and let's change our color again to. I'm going to go maybe charcoal. All right, the distance between the bottom surface. All right. Now, basically, we're just going back to distance equals speed times time. Okay. All right, so it's actually 2D equals 2.98 times 10 to the 8 times the time difference of so 23 milliseconds, 23.6, but I wrote 2.36 times 10 to the -4. Okay, and I'm just going to stick that in my calculator and work it out. Okay, 2.98 E8 times 2.36 E-4 and divide that by 2. 38,164 meters, which is about, round to the appropriate number of significant figures. Everything was given in 3 sig figs. So let's write that as 3.52 times. All right. Whoops, don't put that, just one place there, please. Okay. Back to my charcoal pen. Okay, times 10 to the 4. There we go, meters. Don't forget your units. So far, so good. Okay, Magellan was put in a circular polar orbit around Venus with a period of that. Okay. Okay, why a polar orbit was used for surveying the surface of Venus? Now, I assume it was not necessarily retrograde, didn't say so, but you can observe same kind of north to south strip from low orbit. And that implies a high. I assume it's, well, not its own. It may have had a camera as well, but the point is essentially in the same kind of thought process. that this microwave beam is going to be more effective if it's closer rather than further away. So having a geostationary orbit. Actually, well, that's a little bit more complicated because we're talking about Venus. I'm not going to get into that. That's something I'd assume that's not what they're talking. I assume this is what they're talking about. Venus rotates on its side, and just a point of interest, it rotates on its side, and its day is longer than its year. So what we think is actually polar orbit is actually its equatorial. It's like Earth's equatorial, I would imagine. Sort of, depends which way you go. A little bit complicated. I could draw you a picture, but I think we just move on. I think that's what we're after. Okay. All right, so we want to drive that formula. All right, that's not too hard. All right. Okay, so we got those two. We don't even have to find the equations on our sheet. So v squared, I'm just going to go straight in and square this, equals 4 pi squared r squared on t. And that's also equal to, if you squared the other equation, g m on r. Okay, rearranging this. Times that across, 4 pi squared r cubed equals t g m. Sorry, I forgot the square there. Whoops, don't forget that. Okay, now rearranging this finally. R cubed equals t squared g m on 4 pi squared. There you go. Using the equation from part 2, calculate the radius of Magellan's orbit. All right, we can do that. The mass of Venus is this. All right, so let's go for this. All right, R equals the cube root of, all right, now what was the t? T was 5.64 times 10 to the 3 seconds. Times 6.67 times 10 to the minus 11 times oopsies, I've done it again. Get to my pen. Charcoal, please. I don't want that. Go away. Charcoal pen. Okay. Let's make my cube root bigger. There we go. Divided by 4 pi squared. Now let's see if that works. At 5.64 E3 squared times 6.67 E neg 11 times 4.87 E24 divided by bracket 4 pi squared, close bracket. And then take the cube root of that, so power of 1/3. Okay. The answer I got was, all right, write that in scientific notation, ends up being 6.40 times 10 to the, 10 to the 6 meters. All right. So that sounds a bit old. It's at least in the order of creating an order of magnitude. I don't think I've made a mistake here. Also, copy something down. Okay, moving on. Okay, conservation of momentum. This might be tricky for me to pull off on here, but we'll see how we go. The motion of three pucks on the air table is shown in the multi-image diagram below. The pucks, which magnetically repel each other, were held together and were stationary before being released. The mass of puck A is m, the mass of puck B is m, and the mass of puck C is 2m. Okay, when the pucks are released, they move away from each other. As shown in the diagram, the time between each image is constant. So that means the space between these is kind of if you join up those two dots, you can use that as your velocity. Okay, but we've got to use law of conservation of momentum. On the diagram above, draw and label the momentum vectors of each of the three pucks as they move away from each other. Now, A and B have a mass of m, and C has 2m. Okay, so what I'm going to do is this is going to look absolutely awful because I'm not going to be able to do straight lines. Actually, let's have a look. I probably have tools on here to draw stuff, my tools. All right, what have I got? What do these do? Sorry, I'm learning how to use this program while I'm trying to answer a question. But as I made my excuses as to why I was going to do this freehand with a camera, as I mentioned before. Okay. Do I have a drawing tool of this? Like a line drawing tool would be brilliant. Okay. Measure. I've got a lot of tools. This program is meant for like all sorts of things, for CAD and all sorts of stuff. So if I actually learn how to use this properly, it'd be very effective. But all I want is just a like a paint line drawing tool. Okay, yep, arrow. Actually, why not? Let's see if that works. Okay, so I'm going to do this with the mouse, and we'll see how we go. Now, puck A and puck B have massive m. So yeah, that's brilliant. That is brilliant. Okay, so we've got that. All right, now, so I'm taking one of the velocity vectors to be, just have to keep them in ratio in terms of mass. Now, the velocity vector is can be just done between two adjacent positions because they're all the same amount of time. So distance on the same amount of time is your velocity. So that's a velocity vector there for m, for puck A rather. And because essentially puck A and puck B is just going to be joining adjacent ones, whereas puck C I'm going to join two. And the reason for that is because it has twice the mass. All right. Now what they've drawn here, here, and here, I don't think they're actually velocity vectors, although this one does appear to be longer. Actually, I don't know what, they're just directions, I think. All right. So how did I do that? Okay, mark up lines. Okay, so from the center of that one, check a different color. All right, so we've got that. And then one more. Okay, baby blue. Okay, then this one is going to go, not just adjacent one, but down to there. Okay, so you do that with your ruler and pencil. Okay, now I didn't do a too bad of a job with that. So that's the 3 marks for that one. The A of the vector diagram determine whether or not momentum was conserved when the pucks were released. Now I'm just going to have a look to see if I can actually. Now you've got to basically transcribe these. So basically the idea is, let me just write this out in pen. Okay, so the idea is, the question is, if locum applies, then momentum A plus momentum B plus momentum C equals 0. Now, the easiest way for me to do this is to observe this. Momentum A plus momentum B equals negative momentum C. So I'm going to see if that works. All right, so what I'm going to do is I'm going to copy these out. Oops, I just drew on that. No, I wanted the hand grabber tool. That's what I want. Okay, let's see if I can just do a copy paste. Of course, when you do this, you have to actually copy these out using some sort of drawing. It's not too bad because part A and part B are vertical and horizontal respectively. So let's just grab a copy of that one as well. Come here. Come here, you. There we go. So let's do a vector sum. Okay, and with momentum C. Now, can I just reverse the order? Well, for the sake of purposes, I mean, we can just see it. They join up, essentially. I mean, this is actually momentum A plus momentum B is momentum C, which actually should be negative C. Well, all three equals 0. Now, if you know your theory from vectors, vector proofs in specialist maths, you know that the sum of vectors equals 0 is a closed bound object. All right, but if you separate them out, yeah, if you do the vector sum, let me just draw this over the top. Okay, the vector sum of PA and PB, the vector that I drew as a vector sum is that going up that way, and that's PC, or negative PC actually, because it is the opposite direction. Yeah, proof. Yeah. So yeah, that was actually when I discovered that arrow tool, that was very easy to do. All right, so this software is actually pretty good. All right. Okay, we started this, we've done about 45 minutes of this so far. We've done 6 questions. Just out of curiosity, how are we doing for time in terms of this? Yeah, look at the front of the exam, just why not? Let's just go to the front of the exam. Does it have the, am I thinking, no, it's not. It doesn't have the marks of all questions on the front like the math one does. No, I won't bother with that. Okay, no, too far. All right, let's see how far we get. So we're now on to electromagnetism. An electron in a hydrogen atom orbits a proton at a radius of this. Determine the magnitude of electric field created by the proton at the radius at which the electron orbits. Okay, so you're working out the electric field. Now, this is for point sources. So the equation is this. 4 pi epsilon naught Q on R squared. Now, that whole set of values there is 9 times 10 to the 9, and the charge of the proton is 1.6 times 10 to the negative 19 over the distance as stated squared. Okay, so let's work out that. 99 times 1.6 e negative 19 divided by 5.29 e negative 11 squared. 5.15 times 10 to the 11. Okay, that's newtons per coulomb. All right, there we go. Moving on. The diagram below shows a positive charged conductor with a sharp point near a neutral metal plate. Okay, I'm going to butcher this, but I'm going to try my best. All right, now, you're going to get electric field now. What is it? Okay. Positive charge conductor. Now, I'm not going to draw the positive sign. I'm going to make a complete mess of this. But what we're going to see, remember, there's a lot of essentially charge concentrated at the sharp point per unit volume, if you imagine that. Because charges, or the excess charge is built onto the surface, pushed out by just the charges in the conductor spreading themselves out. The excess charge wants to push away from the other excess charge. All right. So why don't we just draw what's going on here, because that's going to be pretty simple. Okay, sort of. I'm not going to draw too many lines because I'm going to make a real mess of this. But remember, charge I didn't do that one too well. Actually, let's redo that one. Okay, charges meet the conducting surface at right angles. Get the pen going again. And the radius of curvature of this part is pretty consistent, so it's all right because it's kind of circular in that kind of way. All right, so these should be kind of evenly spaced. All right, but now we get a sharp point here, so we get a lot of lines. That's one that's going to go straight over there, and you're going to have a lot of ones. Whoops, why it keeps doing that? Pick that up. Yeah, as I said, I'm going to butcher this. I'll try my best though. So you get a lot of field lines coming out of the sharp point. I said you're going to do stuff like this. And I've butchered both of those. Try again. Okay, I need to make this come out at right angles. So it needs to go like something like that. Yeah, you get the general idea. And just continue that. I can't do anything better than that. Unless I had some sort of, if I had a stylus or something, I might be able to draw it better. But yeah, I wish I had my camera. I could use a sharp pencil and sketch that pretty good. Okay, the idea is this very sharp. Okay, so you got a lot of positive charge here. So it'd be built up of negative charge on here on the plate. So thereby, that's why you get this overall field effect in that sort of shape. Okay. All right, some spark plugs used in motor vehicles have electrode with sharp point shown in the image below. Describe how the strong electric field caused by a positively charged electrode, a sharp point can cause current discharge. Okay, so main points is sharp point. I've lost it again. Strong electric field at that point near. So you, I know, so you charge essentially you tract you charge molecules And like the air particles around there will end up charged, particularly polar molecules will be attracted to the point of the strong electric field. And once they come in contact, they would become charged through conduction and then charged particles. Discharge away from sharp point. Okay. Moving on. Okay, Teletron tube is a device used to accelerate electrons as shown in the photograph below. Electrons are deflected when they enter the region between two parallel plates which a potential difference has been applied. Explain why electrons will experience an electrostatic force of constant magnitude when they are between two very long parallel plates, which are a constant potential difference being applied. Okay, inside inside infinite plates, field strength is uniform. So it implies electrons experience constant force, because F is equal to EQ. So if E is constant and its charge is constant, then that's, well, actually negative. It's the other direction. I might drop the effector sign. There we go. Okay, the diagram below shows point A, which is midway between conductor 1 and conductor 2. In conductor 1, there is a current I, which is directed towards the bottom of the page. A current of same magnitude flows in conductor 2. But okay, I was going to ask what's the direction, but that's actually the question for us. Okay. All right. So we've got current 1 going down. Now, let's consider that. I'm going to use a couple colors for this since I've got the opportunity to do so. I'm going to make this pink. Okay, so this is my pink wire. And this one's going to have, okay, if you think about your right-hand curl rule, the field strength, it wraps around the wire, but does so in such a way that the magnetic field strength will be coming out of the page like this. Okay, so that's what your B will be doing due to 1. So that's kind of B number 1. Okay, now to get that to work opposite, so let's think about the other one. So I'm going to make that fluoro green. Okay, so conductor 2. Now to cancel that, you're going to have the magnetic field strength go the opposite direction. Now, reverse engineer the concept of that with your right-hand curl rule. So you think your fingers curling into the page in the middle. In that case, your thumb will be pointed down. So that one, the current is also down. Because it's positioned on the other side, you end up with the opposite effect, the opposite direction of magnetic field strength. So that's B2. Think I'm thinking B1? I think I am B2. Let's use opposite. Okay. So applying, let's go back to a happier neutral color. Let's go back to our blue pen. Okay. Applying right hand curl rule. Okay. B at, so I'm talking B vector at point A is out of the page due, oopsies, I have to spell, due to conductor 1. I don't know why, just call it wire 1. No, it has a current anyway. To cancel force B, the other B, actually it's not really force 4, there's no, okay, I'll just say to cancel this. Again, sorry. Due to conductor conductor, forget it. Conductor 2 must be into the page. Implies I2 is down by the right-hand rule, but I've already stated at the start. Okay, that's it. That's good enough. Okay, question 10 now. Let's have a look, make sure everything's kosher with the stream. Somebody's watching this, so that's all well and good. Okay. I hope that's been playing. That's screen sharing. It's not working. Just trying something out. All right, never mind. Okay. Alrighty. All right, moving on. Question 10. Diagram below shows a cyclotron that is used to accelerate positively charged ions. Okay, checking one more thing actually while I'm here. Okay. No, moving on. Moving on. Okay, back to this actually. Here we go. The diagram below shows a cyclotron that is used to accelerate positive ions. So alternating power supply, magnetic field B. Okay, ion of mass 33.10 to power. Okay, has a radius. All right, so here's some numbers here. Calculate the kinetic energy of the ion as it leaves the cyclotron. Now, what page are we on? Page 18. Okay, so you can go back to your equations and you can find this one. So this is final kinetic energy for cyclotrons. Okay, which is on the second page is that equation there. All right, so Q squared, B squared, R squared on 2M. Oops, that's right. K equals Q squared B squared R squared on 2M. And stick all of the numbers in and come up with the answer. So there's only 2 marks. That's very easy. All right. I'm not going to write out all the numbers that you're certainly welcome to. And suggested to, it's actually better than you substitute all the numbers in and do the calculation rather than just copying out the equation. I'm copying out the equation for just demonstration purposes. E negative 19 squared times 1.2 Tesla squared times R, which is 0.32 squared. Okay, divide by 2 and divide by, is that right? 19 squared B squared R squared on 2 times, oh yeah, divided by the mass, here we go. 3.3 negative 27, oops, 27. Okay, so I've got an answer of 5.72 times 10 to the negative 13 joules. Okay, so it didn't ask us to do it in EV or anything, so I'm going to leave it in joules. That's good enough for me. The kinetic energy of an ion as it leaves a cyclotron does not depend on the potential difference between the Ds. Excuse me. Explain why the ion gains kinetic energy every time it moves across the gap between the Ds. Now the Ds have an alternating E field. Now the period is constant. Basically, every ions oopsies. Okay. I have to write the whole thing out. Everyone. So the ions move back and forth from side to side as they go in their little circular paths. Ions are accelerated with every path. Okay. Explain why by increasing the potential difference between the Ds has no effect on the kinetic energy of the ions that leave the cyclotron. Okay, now you can explain this a couple of ways. There's 3 marks. All right, you can go back to that equation. You can see it's not part of that. A bigger distinction. Okay, K max does. Oh, I should say is not. Or does not depend, or is not. I say it does not depend. Or is independent of. Sorry. Kmax does not depend on delta V. Okay. Or, and more to the point, essentially, it's dependent upon R and a few other things. Basically, if you had a higher delta V, you would gain more kinetic energy for every pass. So basically, it would imply that you would have a larger radius sooner, and you'll be out of your cyclotron sooner. So, yeah. Well, I get that's the explanation. 3 marks. Okay, well, whatever. Let's put that in there. Okay. If delta V was increased, more gain in kinetic energy. I'm abbreviating this because it's really hard to write. More KE per pass, and that infers will reach R max. So there's a certain okay, sorry, I'll write that out again. Will achieve the maximum radius with less passes. So essentially, you're achieving your R max. So that's as much you can do. If you look back at the formula, yeah, that's one of the major features. There's also B, and there's the rest of the things have to do with the particle you want to accelerate. Now you want to accelerate the particle for a particular reason, generally to make a radioisotope or whatever you have to do. So usually they're fixed in terms of what you want to achieve with it. But your B, you might replace the magnets, make that stronger. But your R, it has to do with the physical design, just how big this distance is here. So that's your R. And the bigger you make your cyclotron, so if you want to make really high energy particles, theoretically, you can just make a larger cyclotron or get a very, very strong magnetic field, or both. There's limitations to the cyclotron design, but that's not really in the scope of the course. So I hope that makes sense. Basically, increasing your potential difference of your electric field just means it's just going to emerge with less passes. So you get your particles accelerated quicker, but not with more kinetic energy, final kinetic energy. Okay. Let's have a look. Okay. I'm going to go for another 20 minutes or so. So see how many questions we can bang out between now and then. An experiment was conducted to investigate a force on a current carrying conductor in a magnetic field. The diagram below shows the conductor in the magnetic field of magnitude B equals 0.3 Tesla, which is directed to the right of the page. Now, my students were having a hard time with magnetic fields which were not directed into the page. So I have to go through the solutions to their test with them. However, let's have a look at this. The length of conductor in the magnetic field was 0.55 meters. Got your amperes current flow through the conductor, causing to experience a force directed into the page. The magnitude of the force is measured to be this. Okay, now is into the page, force is into the page. All right, so force was into the page. All right, so your palm is there and your fingers will point in the direction of the magnetic field strength. Now, that implies that the current flows this way because that means there's a component that's perpendicular. Essentially that's the I delta L. Well, I could draw it off the end of this. Actually, let's just do that. Sorry. Okay, let's draw it from here. I'm just doing that because that's where the angle is. So that's the I delta L sine theta. That is the component of the current element which is perpendicular, and you've got the component which is parallel, which has no force acting on it. So that's the I delta L sine theta. So yeah, it must be going essentially up to the right. It was going to go, or it's either up to the right, down to the left, if you're following the direction of the wire. But that's the one that corresponds to having a component of Yeah, if you put your thumb in the direction of that blue line and fingers in the direction of the magnetic field, your force is into the page by the right-hand palm rule. Okay. All right, so we've drawn that on there. Determine the angle theta between the conductor and the magnetic field. All right, so you've got F equals B I delta L sine theta. Okay. All right, so let's just rearrange that because I don't want to keep running out numbers. Sine theta equals F over B I delta L. Okay, theta is equal to the inverse sine. Now I'll start putting some numbers in. Arc sine or inverse sine of 3, the force was 3.8 times 10 to the negative 3 newtons. Okay, we had a Tesla of, what was that? Tesla of 0.3 Teslas times current 0.05 times and times by length, which was 0.55 meters. Okay, so let's work that out. 3.8 e neg 3 divided by bracket 0.3 times 0.05 times 0.55 close bracket. Okay, the division of that is 0.461. Now, inverse sine of that. So I'm going to go the whole hog in one hit. 27.4 is the angle I got. Sorry. Try it again. Got the decimal place wrong. 27.4 degrees. Okay, so that's the angle. There's a point there. It didn't come out right. There we go. Conductor was then placed so it was perpendicular to the magnetic field. The force on conductor was measured for currents of different magnitudes. Okay, so we got that. Okay. Explain why the graph shows the presence of a systematic error. All right, so let's have a look at, so it's placed perpendicular. How is it measured? Okay, basically, as now, because it's perpendicular, as F equals B I delta L. So force is perpendicular to, force is proportional to current, and essentially force versus I should pass through the origin. So we explain why the graph shows the presence of a systematic error. The path of the charge, okay, so an entirely different question, isn't it? Okay, so that's all we had to do for that. Okay, fair enough. The path that a charged particle takes in a magnetic field can be used to determine the mass of the particle. The particle of charge 3.2 times 10 to the minus 19 coulombs enters the magnetic field 0.14 Tesla with a velocity of 4.0 times 10 to the 5 meters per second. Calculate the magnitude of force on that particle. Okay. Now the formula for this is F equals, so it enters perpendicular, BQV. Okay, so we've got 0.14 Tesla times charge of 3.2 times 10 to the negative 19 coulombs times 4 times 10 to the 5. Okay. 0.14 times 3.2 e negative 19 times 4e5. Okay, okay, for 3 sig figs, 1.79 times 10 to the, it's actually probably should do it at 2 sig figs, but that's all right. So everything else is in 2 sig figs. Times 10 to the negative 14 newtons. Okay, there we go. Explain why the charged particle moves with uniform circular motion when it enters magnetic field velocity that's perpendicular to the magnetic field. Okay, now force is a right-angled, so you should write this out in words. I'm doing it in symbols, this is annoying writing with my finger, to V. So force magnetic implies, so if your force is right angles to your velocity, that implies uniform circular motion. Actually, I'll just put a note that the other reference they want 3 marks is the right hand. The rule that states that is right hand palm rule. Okay, let's reference that. Derive the expression. Okay, so the 2 formulas that we're going to use for that is F, the one we just stated before, F equals B Q V, that's your magnetic one, and your centrifugal force is your acceleration, A is equal to V squared on R, but times by mass, by Newton's second law, mv squared on R. Okay, the equation between the two, BQV equals mv squared on R. Okay, rearranging that, so times your R across, actually we can cancel the V straight away, like that. So divide 1V on both sides. All right, so times R across, we have R, B, Q equals mv. R equals mv over bq. There you go, got it. Well, it's not quite as it's stated, but it's equivalent. BQ, QB, same thing. The diagram below shows the circular, the path of a charged particle is entered a magnetic field, magnitude B 1.4 Tesla, which is directed into the page. The initial velocity of the particle is such, perpendicular to the magnetic field. The particle has charge. Okay, you've got charge. All right, use the diagram above to determine that. They've got a little ruler here. So the ruler goes, essentially there is 12 centimeters in diameter, as you can see here, thereabouts. Okay, so R is equal to 6. Or 0.06 meters. Okay. So we just used the formula to work out R. So what do we need to find here? Find the mass. So rearranging that in terms of mass. So we get R BQ on V. Okay, so we got 0.06. Okay, Tesla 0.14. Keep running these as little sixes. I'm gonna fix that. Times by charge, what was it? 3.2 e negative 19, and 4 times 10 to the 5. So what was it, 3? 4, sorry. Okay, there we go. Okay, 4 times 10, 5. Work that out. Okay, 0.06 times 0.14 times 3.2 e negative 19 divided by 4e5. Okay, so I've got a mass of, that makes sense. I mean, we've got 2 atomic charges here. I think this might be an alpha particle, but I'm not sure. But it's that kind of mass. And whatever it is, it has 2 protons. So I imagine it's some variation of helium. So one of the isotopes. And that's the sort of order of magnitude of a light nuclei. Determine the sign of the particle. Okay, now its force is that way at that point, and its velocity is that way. And you can see B is in the page. So let's engineer that. Oh, that's assuming that it's that it is positive charge. Yes, that confirms. You use the right-hand palm rule. If your thumb's going to the left and your palms are heading down, your fingers do point into the page, consistent with B. Now, if that wasn't consistent, you'd have to flip. Like if it was a negative charge, you would point your thumb opposite the direction of velocity. But that's inconsistent with the direction of force if I'm still pointing my fingers into the page for the magnetic field. Okay, so it is positively charged. Okay, positive charge. Okay, we've got 5 minutes left. So let's see if I just get through question 13. I might leave it there. State the direction. Actually, let's have a look at the start of the question. Sorry, read this out. The photograph below shows a television antenna being positioned so it receives horizontally polarized electromagnetic waves. State the direction of oscillating electric fields in a horizontally polarized. Okay, well that's the electric field is also polarized horizontally. If it's the magnetic field, it's at right angles to the direction of polarization. The antenna shown in the photograph above is oriented to receive transmissions from a nearby city television channels. They're the orientation of an antenna that will receive transmissions from country television channels a large distance away. All right, so usually is they're vertical. And the reason for that is because at 9-degree polarization, the signals do not interfere. Because there's no component of the waves which increase or decrease electric fields if they're at right angles to each other. They don't interfere in a constructive or destructive manner. Okay, I spelled that wrong. Constructively or destructively. Okay, I'm going to leave it there. So I'm just going to make a note to myself that I am on to question 14. I'll probably continue this in a week or so. So how did we go? I spent 90 minutes on that, and I went to question 14. So I taught my way through it. Okay, so what is part? Now, they recommend part 1 is 75 minutes. So I'm talking my way through this, and I'm playing around on a computer. So let's have a look at where is... you don't have to, obviously, when you do the exam, you don't have to describe it. So that's why I took longer than what this exam should actually take to do. So I can just scribble out the answers. Actually, I'm pretty much, okay, that's part 2 of section 1. So if I finish that question, I would actually be, yeah, 15 minutes over time. Yeah, as I said, you don't have to explain this to somebody and do it on computer and stream it. So that's easier. It's going to take me a little bit longer to explain it than it is to do it. So when you get a good grasp of these questions, most of them you should be able to punch out very quickly. All right, so still got that one. What else we got to do? Have a look through some of the other questions. All right, so now we're going through interference and things like that, photons, and parts of the course that now we're getting to parts of the course that I haven't actually covered with my Year 12 class yet this year. But I probably will finish off, at least attempt to finish off the rest of the exam in 2 weeks' time. But I'm going to see how this turned out. I have a bad feeling that something in the recording has gone well, has not gone well. All right, but anyway, I'm saving that. And I'm going to come back to this. And what's going on? Oh, I've closed it. That's probably going to close it down. Okay, well, I'm going to stop recording now. And all right, well, see you next time.